Okay, this short video is about using autograph to plot a straight line graph. Here's a set of data and we're going to have a go at plotting this data using autograph. The first thing to note about this data is that on the left-hand scale, this volume here is a very inconvenient scale. If we're going to plot this on a graph, 0.0025 plotted on a graph, 0.00258 and so on plotted on the graph. How would you set the scale to do that, particularly if you're doing it by hand? Well, if we move the decimal point 3 places to the right, we'd get 2.5 in the first set of data here. And if we moved it 3 places to the right in the next set of data, we'd have 2.58 and so on. But where it really is back here at 0.00258. So what we can do is set another scale, or rewrite this data set rather for the volume on our set of table, and this will be the volume measured in milliliters, but this will be times 10 to the minus 3 milliliters. So now, instead of 0.0025, I'm going to write 2.5. So that means 2.5 times 10 to the minus 3 milliliters, which is what we've got if you think about it on the right here. Again, looking at this, 2.5 times 10 to the minus 3, 1, 2, 3, will take us back to there, the correct place for decimal point. So the next one, I'd have to shift that 3 places to the right, and so that would be 0.00258 would be 2.58. The next one would be 2.66, and so on. 2.74, 2.82, 2.9. So, in other words, we've shifted the decimal point to give us a scale that we can plot on the graph, and it would be an easier one to interpret, an easier set of data to interpret. So that's a good trick to use. Shift the decimal point for very big and very small numbers. Now the next thing is we're going to plot this on a graph, or which one goes on the axis and which x-axis, which goes on the y-axis. Generally, the one that we're controlling is the one that goes on the x-axis. So we're plotting 2 sets of data, this set of data and this set of data on the graph. Which one are we controlling? Well, if we look at the temperature, that's going in jumps of 5 degrees centigrade. So that's the one we're controlling. We're heating up this gas and recording the volume of the gas every 5 degrees centigrade. So we're controlling temperature. So the controlling variable, the independent variable, goes on the x-axis. So that's the independence variable. The dependent variable, which is in this case the volume, and it depends on the temperature, so that's why it's called the dependent variable, goes on the x-axis. The one that we're observing, that we're looking at, goes on the y-axis. This is the dependent variable. Sometimes you need to do it a particular way around. In Ohm's law, for example, we would use Ohm's law to find a resistance, and that's voltage divided by current. So we always put voltage on the y-axis and current on the x-axis, so that when we divide the voltage by the current, we get the resistance. So sometimes we have to do it a particular way around, but often it's up to us which way around we put the axes, and we always tend to put the independent variable on the x-axis as a general rule. So I'm going to plot these 2 variables on autograph. So what I do is I start autograph off, and I'm going to put my data set in. So where is the data set? If you go to this button here, that button there, the enter data set. I enter the data by putting in the data. So the first set of data is going to be what goes on the x-axis, so that will be 60 degrees centigrade here, and y will be 2.5. So enter into the data set 60 for. If I want to go to the next data point, I just hit return, and now it goes to the cursor flashes by y, 2.5, hit return, and so on, and put the data in. So I'll just pause this and put the rest of the data in. Okay, so I'll put the rest of the data in. There it is, up to 2.90. You don't need to put the 0 in, but I have done for completeness. And there's the data points, and you can see that they're all squashed together. So I can use the zoom box tool, which is this one here, and put a box around my data, and it will zoom out to those data points. That's one thing I can do. Let's zoom back out again using this one, the whole lot, back to there again. Something else I can do, if we look at this data set here, these data points here, along the y-axis, they're all over a very narrow band within the y-axis. So if I want to zoom in on the y-axis, that will stretch these data points out. And that's this button here. So if I zoom in on the y-axis, and every time I zoom in, I click roughly where the data points is, then it'll keep the data in the middle of the screen pretty well. Now you can see it's looking more like a line at 45 degrees. So now I can again use this zoom box tool to zoom in on my data points, and there are my data points. So I can get my data points and I can zoom in on them like that. Let's zoom back out again using this one here, back to here again. What I'm really interested in is getting the equation of this line. So what I do is I put in the equation of the line. So put in this box here for enter an equation. I type in the equation of the line. Y equals mx plus c. And if we think about this, y equals mx plus c, m represents the gradient of the line, and c represents the point at which it cuts the y-axis. So if I hit OK, I get this red line here, which is a red line with gradient 1 and y-intercept 1. By default, the y-intercept is always 1 and the gradient's always 1. If I want to change the values of these constants, I use this box here, and so that allows me to change the values of c or m by just clicking on them like this. If we look at the red line, we can see the gradient's far too big, so let's have a go at changing the gradient. If I hit this, I make the gradient a bit smaller. You can see sometimes if you hold it down, it just carries on. That's a bit, doesn't always work. And you also see that it's coming down very slowly. So I can change the step size, coming down instead of steps of 0.0001. Let's change it to 0.01, and then reduce the value of the gradient. And you can see this line coming down towards it. Still quite a small step size, so let's change it coming down in steps of 0.1. Click on it like this and you can see the gradient changes. Now it's far too big a step size. Note also if I go negative, the gradient goes negative, so positive gradient. Let's change it to 0.01 again. Reduce the value of the gradient. What I'm after is trying to get the gradient pretty well parallel with the data points. So now I need to adjust the value of c. Note that at this point the line is cutting the y-axis at 1, which agrees with the fact that c equals 1 because c represents the y-intercept. I want to increase c to bring the line up towards the data points. So now using this expanded out, zoomed out scale, I can get the line roughly where I want it to be. What I want to do now is again using this zoom box in zoom box around the data. So now I can fine tune my values for Y and C to get the values. So let's change M. Let's make the step size a bit smaller. I usually try and get the line roughly parallel with the data points, and then change C to bring the line down onto the data points. Changing too slowly, so let's change that to a bit bigger step size. Again, now we can see it's not quite parallel, so let's again go back to M, make the step size a bit smaller, and again the gradient's not quite enough, is it? So I need to increase the step size slightly, make it a more small step size. Again, adjusting it till it's roughly parallel, which it looks as though it's pretty well now, and then change C. So I need to increase the step size a bit. We're getting there. So you can see the idea. Okay, I might change M and C slightly now, and you could zoom in again on these data points. But the idea is to get values for M and C by using autograph, and that will then give you these values for the equation of the line. Okay, if you look at the notes, you can see now that I've actually put into your notes one I did earlier, but I've zoomed in on M and C to find those values. So M turns out to be a 0.0159, C turns out to be about 1.5508. Well, that gives us our values. So we've got M equals 0.0159 and C equals 1.55. That's three significant figures. So at this point we have to be careful because the value of M is not quite right. If you remember how you get M, we take our line and we draw in. Basically what we've done is drawn a right angle triangle here. That's how we do this if we're plotting this graph by hand, as you might remember. And so we divide Y by X. But if you remember, going back to our table, we've actually need Y to be times 10 to the minus 3. So the Y value should be a factor of 10 to the minus 3 times smaller. So if I go back to this value here, this Y value should be another factor of 3 lower than that. So I need to take that into account. This is times 10 to the minus 3. So if I divide Y by X, Y is 1,000 times smaller, so that means the gradient's going to be 1,000 times smaller. So this value here should be times 10 to the minus 3. So M is actually 0.1234159. 4 zeros 159. Probably what I would do at this point was actually to use standard form to make this a more straightforward number. So I'd probably call that 15.9 times 10 to the minus 6. And the units would be whatever units Y and the Y and X axis are measured in. So let's go back to that. That would be milliliters per degree centigrade. So that would be a gradient of finally of 115.9 times 10 to the minus 6 milliliters per degree centigrade. So remember, this is about changing volume of gas with temperature. So the volume is changing by 15.9 times 10 to the minus 6. Well, I put 16, 10 to the minus 6 millilitres per degree centigrade. What does the C represent? C represents the volume of the gas before we started to heat it up. This is the volume of the gas at 60 degrees centigrade. And if I wanted to write down what the equation for this change in volume is, remember we've got this, we've got y equals mx plus c is the equation for this. Well, what is y? Y is the volume of the gas. What is m? It's 15.9 times 10 to the minus 6 times x, which in this case is the temperature, plus C, which is the temperature at 6 degrees centigrade, which is, sorry, volume at 60 degrees, which is 1.55, times 10 to the minus 3, of course, because again, this 1.55 is taken off that scale, which should be times 10 to the minus 3. So there we go, using the autograph to find the equation of the line. Compare this little video with finding the equation of the line using graph paper and see if we get the same results.